Good day to you. Hello. So we are going to start talking about a group of curves called conic sections. And conic sections are not a function. We've seen actually two of them already. We've alluded to a third one with some different things, and you've actually seen a fourth one in past experiences of Algebra 2. Now, the idea behind conic sections, the root word here is cone. What happens is if we imagine we've got a point and a line passing through that point. If we take some axis here, this axis of rotation, and I'm going to rotate this line around this axis, what's going to happen is that rotation, as that rotates around, so as we start spinning this line around, it will generate this three-dimensional double cone that has the connected at that point. I'm not going to care about the names of like the edges and the napes and the different sizes of the cones. But we're going to look at how we can take this item and create different curves out of it, a whole family of curves. These are going to be, and we're going to look at different transformations that we can make, how to graph them, and the different properties. So, conic sections, we take a line going through a point, we rotate it around some axis, it creates a double cone. Hence, and how we're going to find, we're going to change this up to find what we call some conic sections. After this, now, we're going to look at specific curves. We're going to find these by slicing the cone in different ways. First of our conic sections is what we've just been looking at with polar coordinates, circle. If we're going to take a plane, a flat piece like a paper, and slice through this cone, we're going to slice perpendicular to the axis of rotation. So if we take a plane and slice through our cone, what we're going to get is a circle. Think about like the base of a cone itself. So slice through. That cross section that comes out is going to be a circle. That's our first conic section. Our second is if rather than slicing perpendicular to the axis of rotation, if we start slicing at an angle, well, it's going to be kind of stretched out, not perfectly in line with the cone, but what's going to happen is it's going to stretch out. We get an ellipse. So if I take my plane and I slice through the cone at an angle, it's going to intersect. Well, it's kind of like a circle, but it's going to be stretched out depending upon the angle at which we do this. So we have an ellipse there. It's kind of a stretched out circle. Next up, our third conic section. If we slice at an angle equal to the edge of the cone. So we take our plane, slice through there. That intersection is now going to intersect the base of the cone. You can see that, okay, well, we've got this point over here. It's going to come up the side of one portion of the cone. It's going to go around, come up the side of the other cone. We've got a parabola that's formed. And our fourth, if we take our plane and we just keep on switching that angle, if we go greater than the angle of the side so that we intersect both the top and the bottom portion of the cone, we get what's known as an hyperbola. So hyperbola, our plane comes down, it's going to intersect both sides of our cone there. And what happens is we've got this double figure here, we call a hyperbola. And there's going to be boundary lines in here. And you've actually seen hyperbolas, hopefully last year in Algebra 2, something like y equals 1 over x. Our rational function is actually an example of an hyperbola. Now we're going to focus today looking at circles. We've seen this already looking at polar coordinates. And our equation, the base equation of a circle from polar coordinates was just r equals a, where a was our radius. we're going to take this, transform it into rectangular coordinates, our Cartesian coordinates, and see how we can manipulate that to move our circle around, change the radius and such. Now, in polar coordinates, we switch to rectangular coordinates here with the equation of a circle. If we square both sides, that gave us r squared equals a squared. Now our substitution in polar coordinates, we know that r squared was equal to x squared plus y squared. Pythagorean theorem, unit circle. If we make that substitution, we've got x squared plus y squared equals a squared, where a is the radius. And, well, we're in rectangular coordinates already. Done. Now, what we're going to do is we want to shift this around. Thinking back to all of your horizontal, vertical shifts, dilations, back to past experience, either with me with the trig functions or previous experience with algebra 2. Think about what happens for our parabola if we had x minus h squared. Well, that would be a horizontal shift, left or right. I'm going to add in y minus k squared. That would be a vertical shift, up or down, depending upon how it was. And so I'm going to label this not equal to a squared, but back to r squared. And this is going to be our general equation, our standard equation of a circle here, where hk is the center and r is the radius. You can't see that. There we go. Putting that again. So our standard equation of a circle is just x minus h squared plus y minus k squared equals r squared. That hk is our center, r is our radius. So with polar coordinates, we were really stuck to the pole, the central point, that 0, 0, the center of the graph. How do we move that left, right, up, down? Well, some of us working with the Polar Design Project asked about that. We had this big convoluted equation. What I was doing in the transformation was I switched over here. We fix our central point, fix the radius, and then we had to switch back to polar coordinates. Reading something like this, x plus 2 squared plus y minus 1 squared equals 16, this I recognize as being the equation of a circle. It's that x squared plus y squared equals our radius squared. Taking from this, I can see that our radius is 4. This is x minus negative 2, y minus 1. So we've got a central point. So this equation gives us a circle with a center, negative 2, 1, and a radius of 4. We could then go graph this. Let's get it in frame. We've got center, negative 1, negative 2, 1. Center of our circle. If our radius is 4, 1, 2, 3, 4. 1, 2, 3, 4. We move 4 units in every direction. 1, 2, 3, 4. And 1, 2, 3, 4. So we can graph. Likewise, if we have the graph of a circle, we can take the center point, plug it back into the equation. If we have the radius, we can substitute it back into the radius, back into the equation. Now this, we've got a perfect square binomial, Hopefully you're thinking back to what we did yesterday. If I switch things around, if we were to multiply this out, we have what we call the general equation of a circle. If everything's all opened up, the parentheses are opened up, we've distributed, we've multiplied out, if we've got x squared plus y squared equals ax plus by plus c equals 0, we say this is the general equation of a circle. Let's go through, find the center, find the radius, sketch a graph of this. Well, initially what I see is the center is not so obvious in there, the radius is not so obvious. We're going to convert back to standard form. Missed an A in there. And that's done by completing the square. I'm going to group the x terms. I'm going to group the y terms. I'm going to take the constant, move it to the other side. Now, completing a square, I need to turn this into a perfect square binomial. I need to turn this into a perfect square binomial. Now, thinking x squared minus 6x, what can we add to this so that this becomes a perfect square? That was our take the b value, -6, divide in half, gets us -3, square that value. So I've got -6 divided in half gets us -3. I'm going to square that. That gets us 9. So I'm going to add and subtract 9. I'm going to do the same for the y. So the y, the b term, the coefficient of the linear term, is 10. So I'm going to take 10, divide that in 2. I've got 5. I'm going to square that. I've got 25. So I'm going to both add and subtract 25. I'm going to do it a little bit different from what I did yesterday. I've got x squared minus 6x. If I add 9, I can also, it should be negative over there, take my -18, add 9 to the other side. If we add the same thing to both sides of an equation, everything's equal. We've got plus y squared plus 10y. If I add 25, I'm also going to add 25 to the right side. That way, added the same thing to both sides, everything is balanced. That factor of completing the square, I can now turn this into x minus 3 squared. Notice that the linear piece in the binomial, or the constant in the binomial, is half of the b term. Y squared plus 10y plus 25 becomes plus y plus 5 squared. Getting back to our standard form of a circle. -18 plus 9 is -9, plus 25 is 16. We've taken our general form of a general equation of a circle, turned it into the standard equation of a circle. That gets us a center, 3, -5, with a radius of 4. Then we can graph it. Try it out.